All right, welcome to our Centripetal Force Lab activity. What we're going to do is actually cause a mass to go in a circle and measure the centripetal force. Remember that the centripetal force of a mass m moving in a circle with a radius r at a speed v is just m v squared over r. So what we're going to do is take this mass right here. We're going to move it in a circle. It's going to stretch the spring out. That will enable us to measure the centripetal force of that mass. So before we even start, we've got a counterbalance here. Once this thing gets spinning, it can easily get out of balance and start bouncing around. So we have a counterbalance here to balance the main mass. But we want to make sure that it's in the right position. So if I just tilt this a little bit, I can see that it's not really in a good position. So I'm going to just shift the masses over a little bit, change the center of rotation a little, like that. Try it again. Just by tilting it, it enables me to see if they're balanced or not. Now it's a little bit more adjustment needed. Still not quite right. I'm going to move this mass a little bit farther out. Oh, that's good enough. Okay, good. The next thing we want to do is make sure that this, oops, always something. I want to make sure that this mass is hanging directly over this pointer. The pointer is what is going to allow me to move the mass out at a constant distance. Now I can see my pointer won't adjust. Oh, there we go. So that the pointer is directly beneath the tip of the mass. There, I'm going to tighten this down a little bit. Now, when I attach the spring, this is a stretching spring. Attach it to the center post. Now, when I rotate the device, it comes to a point where the mass swings out farther and farther. And the purpose of the pointer here is so that I can make the mass be at a constant distance while I take the measurements. Now, what's happening here is what we're going to do is just basically follow the procedure, which is set up the apparatus so the revolving mass hangs directly over the pointer. We just did that. Adjust the counterbalance. We did that. We're going to measure the horizontal distance from the center of the rotating shaft to the pointer. That's going to be our R in this formula. So we want to measure the radius of the circle that this mass is going in when it's stretched out to this position. So that would be the distance from the center of rotation, that's the center of this shaft, to, there's some strings here. Actually, those strings are a little bit tangled. I'm going to untangle those right off the bat here. Make sure it's set up nice and proper. Okay. Okay, so we want to measure the distance from the center of the shaft to where the string is. I'm going to take my measuring stick and measure that distance. From the center of the shaft to where the strings are, which is right about here. Looks like about 20.5 centimeters. Oh, sorry.
Oh, you're fine.
So 20.5 centimeters. That will be our radius of the circle. In meters. So you have the radius in meters what did I say? I said 25.0 centimeters. And we also need the mass of the revolving mass. So I'm going to take that off and measure its mass. Yeah, 200, 300, 400. So it's between 400 and 500. $560. Okay, about 561 grams. So we're going to write that in here. The revolving mass, but it's asking for kilograms. So I'm going to convert 561 grams into kilograms, 0.561 kilograms. Okay. The next step in the procedure is to connect the spring between the mass and the central shaft. Now, what do we need to know? We're looking for mv squared over r. The m and r we just measured. But how do we get the speed of the thing going around in a circle? Well, when an object is moving in a circle, radius r, remember speed is just distance over time. In one revolution, the distance it moves is the circumference, which is just 2 pi r. And the time is called the period. The time that it takes is the period of rotation. So what we need is the time it takes for it to go all the way around once. And you can see on your data page, that's exactly what we'll be recording, the time it takes to make one complete revolution in seconds. Okay, so how are we going to do that? Well, in the old days, we used a stopwatch and timed it for 30 revolutions. But this is the age of modern electronics, so we can use electronic timer, the same kind that we used in the Newton's Law Lab, photogate. What we're going to do, remember how this works. When you reset the button to 0, I have it in the what's called the pulse mode, which means that the first time you break the beam, the clock starts. The next time you break it, it stops. So what we're going to do is have this device run through the photogate, start the photogate, and then stop it one position later, and that'll give us the time for one complete revolution. But we don't want this heavy mass banging into the photogate, so what I'm going to do is I'm going to make a little beam breaker here. Cut a piece of cardboard. I'm just going to attach that to the mass, just like this. I need a bigger piece of tape. So that when it passes through the photogate, it'll break the beam once, and then break the beam again, and that'll give us the time for one complete revolution. This way, if it bumps into the photogate, it won't do any harm because it's just a piece of paper. Okay, now, so all we have to do is to get this thing revolving so that the mass is, oh, just what I didn't want it to do. Also notice that it's jumping around a little bit. So I'm going to get a clamp, a C-clamp, and attach this to the table a little bit more sturdily. Just to make sure it doesn't dance around too much. Like that. Okay. Now the tricky part is making sure that the pointer, that the mass is directly beneath the pointer. And I can't actually see it very well because of all of this paper, so I'm going to trim this down a little bit, give me better visibility, so that when it's over the pointer, I can actually see it. It doesn't have to be that long. Okay, I'm going to practice a little bit. Getting this right over the pointer. What I'm going to do is start the reset button. Now, okay, and I should have a time. Unfortunately, it's not plugged in. Step number 1, plug in the photo gate. There we go. Let's try that again. Okay, I pushed the button, and we have a time of 0.566 seconds. So I'm going to write that for time T1. Let's do it 2 more times so we can take an average. Okay, I'm getting 0.574, which is pretty close. Let's do it one more time. I'm getting 0.563. And since these are so close together, that gives me some confidence that the numbers are good. Now, one question is, what would happen? First of all, this will allow us to calculate the centripetal force. But we'd always like to find a way to check that. How could we check to know that that really is the centripetal force that we're talking about? So we have a way to do that. What we're going to do is take a string, attach it to the revolving mass, put it over the pulley, and hang a 50-gram hanger from it. Now what I'm going to do is add masses to that until it pulls the revolving mass. Oh, something very bad has happened. It slipped. It's not over the pointer anymore. So, as nice as those numbers were, they're not good. So we're just going to have to take that first measurement again. These things happen when you do in the lab. Somehow the whole apparatus slid and decreased the radius, which invalidates all those. So we're just going to do a real quick remeasure of those 3 times. This time we're getting 0.618. So what I'm going to do, I'm just going to cross out the old data, write the new 0.618. Let's look it again. This time I'm getting 0.626, close enough. And there's nothing wrong with crossing out old data to write new data. In fact, that makes your data sheet look more authentic. It looks like real data. Okay, 0.610. Good, okay. Now, what I was getting to previously is how do we check? We're going to calculate the centripetal force from this data. How do we check, get a second opinion of what that centripetal force really is? We're going to put a string onto the mass, hang the hanger from that. And I'm going to put more masses on that to stretch it out until it's over the same pointer, just like it was when it was rotating. Now here's the key point. What actually supplies the centripetal force when this thing is turning? What is actually holding this in a circle? Why isn't it flying off in a straight line? Where does the centripetal inward force come from? It comes from the spring. The spring is the centripetal force when it's going in a circle. So if I can measure how much force it takes to pull the spring out to the same point, then that must be the same as the centripetal force. Let me say that again, okay? The spring is what supplies the centripetal force when it's revolving. So whatever force will pull the spring out to the same distance, that force must equal the centripetal force, because that's the force that the spring is exerting at this point. So I'm going to add masses to the hanging mass until it pulls the revolving mass out to the same point. I'm going to start with 500 grams, added to the 50 grams. You see that's not quite enough. Let me just grab a couple of 2s over here. Add another 200 grams. That'll make 750. Still not there. Add another 2 to make it 950. Still not there. Oh, yes it is. There it is. Beautiful. See, now this weight here is stretching the spring out just the same as it was when it was revolving. So this must equal the centripetal force. So let's count up our masses here. We've got 5, 7, 9, 950. So the hanging mass is 950. And the hanging in kilograms, 950 grams is 0.950 kilograms. Okay, now we have 3 times here. You can take the average. Once you've done that, you can calculate the velocity, which is 2 pi r over t. Plug the velocity into the centripetal force equation, get mv squared over r. That gives the centripetal force when it's revolving. We can check on that by getting the centripetal force from the hanging mass. That's just mg, where the g is 9.8 meters per second squared. So we have two values of the centripetal force. You get the percent difference between those two. In a normal lab, we would be a little bit more elaborate. We would add some masses to the revolving mass, but I'm only going to do a couple of those. I think let's ask the question, what would happen if we added a mass here? Say 50 grams. How would that affect our centripetal force? Well, some of you are probably looking at the equation and saying if you add a mass there, it's going to increase the centripetal force. But if we actually do this, we're still going out to the same position when we revolve this. The spring is still stretched to the same length as before. So wouldn't the centripetal force be the same? Yes, you say, but it's got more mass. So more mass should mean greater centripetal force. But because the centripetal force is the spring, we know that the centripetal force must be the same. So how can that be? Well, the point is, if we increase the mass, and the centripetal force must be constant because of the spring, then the velocity must decrease. It must actually slow down. So let's do this one more time with 50 grams. And you can do the centripetal force measurement again, confirm that it's the same, and also notice that the velocity is different. So here we go. We've got 50 grams added to our revolving mass. Plug it in. And we're going to take this one more data set. Okay, now we're getting a time of 0.664. We have 50 grams now on the mass, 0.664. And notice the time is longer than it was before. What does that tell us about the speed? If it takes a longer time to go around once, the speed must have decreased because we increased the mass. Let's take two more data points. All right, there's one. Getting 0.651. Again, it's greater than it was before. And one more. Okay, this time we're getting 0.629. And now, what if it says M hanging. How much mass would it take to pull this out to the same position? Well, let's do it. Let's see, last time it took 950. Let's put 950 on again. What do you think? Will it be more or less or the same? 950. It's exactly the same. Why? I don't hear you. Okay, why? Because the spring is pulled out the same distance. So of course it takes the same mass. It doesn't matter how much mass you have here. You could put an elephant on this thing, but that's a vertical force. It has nothing to do with the horizontal stretching of the spring. So because the spring is stretched the same each time, the centripetal force is going to be the same each time. So what changes is not the centripetal force, it's the velocity is less. So all I'm going to ask you to do in this lab report, if we had enough time, if you were in the laboratory, we would take a lot more data and you could do a graph of the centripetal force versus the mass and so forth. But all I'm going to ask you to do, for the sake of simplicity, is to compare these two and talk about, there won't be any graphing in this lab, and talk about what effect did it have when we added mass to the revolving mass, and why did it have that effect. The hanging mass will be the same, 0.950. And you might want to compare, that's really basically all you need to compare. Just compare the hanging mass with the centripetal force in each case. And that should just about do it. All right, so again, you want to talk about sources of measurement error, what kinds of things could go wrong to, the biggie, of course, is trying to make sure that while it's rotating, it's directly over the pointer, it's moving so fast it's kind of hard to judge. Also, is it really balanced correctly? And it's kind of difficult to see exactly where this is located and so forth. Anything you could think of that would affect the measurement accuracy. Okay, so that's it for centripetal force. Let me know if you have any questions. Good luck in your lab report.